let's take a stock of what all things we have done up until now, okay, and then we'll see where we move forward. Okay, so okay, so this doesn't work. This is better. Okay, so we all have been talking about vertex cover all the while, okay, and how did we see? Up until now, what we have seen is that, okay, we started with n choose k algorithm, okay, and then we moved to this k plus 1 to the power k algorithm, which with little bit of modification we were able to power k time. And the ideas from here, we said, hey, why not try to find a w so that my solution is contained inside w, and w had size k to the power big of 1 or whatever. This led to the coming up with what I called kernel or pre-processing algorithms. With first we came up with some 2k square edges and 4k square vertices, right? No, k square edges and 2k square vertices. Then we still came up with k square edges, but it was 2 by 3 k square vertices, and then we came up with k square 3k vertices, then we came up with k square 2k vertices, okay. And on the way we saw some nice beautiful tricks, like, so this was like basically high degree argument, okay. This was like degree 2 reduction rule that we gave us, and this was what I called crown, and this was like more like nice crown or much more efficient crown. And for this we did this linear programming based formulation, what is basically called Nehm-Hausser-Trotter theorem, okay. So this is where we were, but we also saw two more things in the beginning before even we came up to this. What was that? There was a 4 to the power k algorithm, right? There was a 4 to the power k algorithm with random separation, and there was 2.27 to the roughly using colorful solution or partition vertex cover, right? So this is what we have learned. So up until now, our benchmark algorithm, benchmark vertex cover algorithm is like 2 power k, and we use this benchmark algorithm to design an algorithm with running time 1.7 to the power n, where n is number of vertices. Okay, right? So if I look at k, so now there are several questions, okay, that we might like to address or try to understand from here, okay. So what are the basic set of questions that we could try to understand, right? One is like, look at k, which was my solution size, right? Right, and then we used n, which was number of vertices, and we know that this is the relation which holds between k and n, okay. So maybe what's a natural question to ask? What are the parameters here, right? Does or is vertex cover FPT with parameters that are provably smaller than solution size, okay. So this is the first thing we would like to ask, okay. So, this is one question that we could ask. Okay. B, we could ask with respect to k, how much more smaller can we go? How much more smaller we could go? Like, in other words, can I go 2 power k to 2 minus epsilon to the power k, for example, right? And like, I am not talking about polynomial dependence anymore, but like from 2 power k, can I go to 2 minus epsilon to the power k, right? I mean, so all these are questions. See, right, I have 1.7 to the power n algorithm, right? Can I go 1.7 minus epsilon to the power n algorithm? Right? I mean, I could ask various set of questions, and the various set of questions could lead to various set of answers. Okay. So, now we will zoom into some of these questions and try to see where we reach. Okay. Okay. So, we will come to this question a little bit later, but now what I want to do is that let us try to understand that. Suppose if I look at our first algorithm that we designed, if we wanted to have a deterministic version of that algorithm, how will we go about it, right? What were the basic ingredients of that randomized algorithm, and what we could do to make those basic ingredients, we could compute those basic ingredients deterministically. Okay. So, what was our algorithm? If you recall, our algorithm was, so our algorithm was based on very simple observation that if we have a vertex cover S of size k, if we have a vertex cover S of size k, then first I can come up with some I star subset of I star set of size at most k, and n of I star is equal to S. Okay. This is what we can come up with. Okay. Why is this true? If you recall correctly, the reason why it was true is that first of all, I can assume that S is a minimal vertex cover. Okay. And why did we, like, what does this help us to do is that it told us that for every vertex here, because it is a minimal vertex cover, there all its neighbors shouldn't be here, because if all the neighbors of this vertex is here, then I can put it this vertex into I with all its neighbors in S, and that S minus this vertex is still a vertex cover, and that contradicts the fact that S is a minimal vertex cover. Now, what that told us that to construct this I star, just pick for every V in S, pick its neighbor in I, pick a neighbor in I, and that is it. That gave you I star. Okay. And then we observed that in fact, there is nothing amazing about I star. Any set, look at I star, any set J that contains I star and contained inside I, neighborhood of J is equal to S, and that is what our. So, how did we design this algorithm after that? After this, the algorithm was fairly simple, that once we reached here, right, what did we say? So, I gave you a clear picture of what we have done and what are we trying to address as we go forward. Okay. So, what was it then? What was the algorithm? Algorithm is fairly simple. What was that? Like, randomly partition the vertex set into two parts, V1 and V2, and what did we compute? Probability that S is here and I star is here. Probability S is subset of V1 and I star is subset of V2 was like 1/4 to the power k, and that is why if we repeat this experiment 4 to the power k and 4 to the power k times with constant success probability, and what is the algorithm? Just after that, output neighborhood of V2. That's it. Okay. Okay. Now I would like to construct a potential partition, but in polytime, not polytime, rather say in some point of time I would like to compute. So basically what should be the deterministic version of this problem? The deterministic version could be output partitions V1, V2. Okay. So what will be a deterministic version of this algorithm? Okay. A deterministic version of this algorithm should be okay. So what is the deterministic version of this algorithm? Okay. So deterministic version of the algorithm will be output a family F, okay, where it is like consists of A comma B is a partition of Vg. This is first thing. So F is a family of partitions of my vertex set. And what else property do I want? Okay. What I want, like ideally, like the most interestingly I would like to have for all x comma y, size of x is k, size of y is k, and x intersection y equal to empty set. Okay. There exists, so for all x y, so the size of x is small, size of y is k, and x intersection y is phi, there exists A comma B in F such that x is a subset of A and y is subset of B. If I can come up with this family, with what is the property of this? That you give me a two sets x and y have size k, their intersection is empty, then there is some partition which respects x y, meaning x is contained inside y, x is contained inside A, B is contained inside y. If I have such family, then my algorithm is very simple. You go over every partition, right, and you try one of them as, so you will try to apply this, because look, it's true for every x y. So in particular, it is also true for your s comma I star. This is also fine. Right? So if we have such a family which is small, and we can enumerate this nicely, then we are done with an algorithm. So deterministic, because I do not know what S is, I do not know what I star is, but all I know about them that they have small size and they are disjoint at this point of time. Then, and what is the property of this family F? That it is, you give me any two sets x and y should be disjoint and they of size k, then I have a property that there exists A comma B such that x is completely contained inside A, y is completely contained inside B. Okay. Does such a family exist?
Why do we need to do this over all pairs x?
Because I don't know what S and what I is.
But then there won't be such a family.
How do you know such a family doesn't exist?
Like if I pick some k by 2 vertices from A and k by 2 vertices from B and like form x, and similarly form y.
No, come again, what you are saying? I don't get it.
So I construct x.
F has many pairs A comma B. It's not a single partition. What I am saying, look, it's a family of partitions, right? And I am saying there exists A comma B in F. So there exists the partition. Right? My question is first, why such a partition even exists? So why such a family exists first of all? Okay. exist. Can you come up with any f? Take all partitions, no? Will that not work? If I take f equal to all partitions, f equal to all partitions of Vg, what's the size of f? What is the size of f? Huh? 2 power every partition. But this is good for every possible x and y. There is no size constraint. You give me any x and y such that x intersection y is phi, right? This is good. So when I write this, I am never using the fact that this f is good for only size k objects. Okay. You get my point? No. So what happens if, okay, so this is absolutely not clear. For our algorithm to hold, we needed a family with this. If we had a family of size 4 to the power k polynomial in n, then I will only output these partitions and we will be done. But there is absolutely no reason to believe that such a family exists. Do you understand my point? Do you at least understand the question? No. Okay. I know that 2 power n size family exists, but 2 power n size family has nothing to worry about x and y. You give him any two sets which are disjoint, I can find y. Just take this in one side, take every other element in the other side, you are done. That also exists because I am taking over all partitions. Okay. So first let me say why such f exists. Okay. Question. Why f of size this might exist? Okay. Okay. So first absorb the question before we even understand the answer. So does everybody understand the question? Okay. So let's try.
This was also the time taken to enumerate all possible partitions in the random separation algorithm.
The random separation algorithm, we just found a partition and we did this. No, I didn't understand.
I mean, I think
This algorithm took 4 to the power k time, right? And succeeded with probability at least say half. Okay. So now what are you saying?
so what I'm saying is like
Why you choose this number time?
Why did I choose 4 power k? Is that your question? No, I didn't choose anything. I said if I want to make this algorithm deterministic, okay, I better output only 4 power k number of sets if I want to meet this running time. Of course, I can allow any f of k for determinism, but if I want to be as good as my randomized algorithm, I better output a family whose size is not more than 4 power k, and I should be able to enumerate in the size itself and then do polytime operations on them to check my vertex cover. That's all that I am saying. Okay. But it's not even evidently clear that why can I come up with some f a comma b with the following property that for all x of size at most k, all y of size at most k, such objects exist. Right? Not clear, no? Okay. What proof should I give? Let me try. Okay, let's do a fun. Okay, this class is going nowhere, but let's go. Okay, let's see how much combinatorics you people know. Okay, I construct this F greedily. Okay, it's not an algorithm. Okay, I'm just giving an existential proof. Okay. That let me first show to you that such small family exist. Is that fine? Okay. It's existential proof. So what I mean by F, let F be a minimal family of partition. Okay. Let F be, okay, rather, okay, let's not do this. I do not want to confuse you. Okay. Let me give you a slightly, start with all partitions of VG, and I'm giving you a way to throw a partition. Okay. Okay. So here is my F A comma B. A is disjoint equal to VG, A intersection B equal to empty set. So basically all partitions, I start with all partitions, and here is my algorithm. If there exists A comma B, if there exists A comma B which is useless, then F equal to F minus A comma B. Okay. Then I delete this. Now I have to need to define what is the meaning of useless. What is the meaning of useless? So useless is with respect to this definition, right? So meaning even in F minus AB, I have this property that you give me xy, I can find you such object, right? Then it is useless, right? So what is the meaning of useless is that even if I throw this A comma B and I am able to maintain the property that for every xy, right, there exists. So what I mean to say, which is useless, okay, if there exists A comma B which is useless, then this. And what is the definition of useless? Okay, for all x comma y, no, if there exists x comma y, mod x equal to k, y equal to k, such that x is contained inside A and y is contained inside B, okay, there exists another A prime comma B prime such that x is contained inside A prime and y is contained inside B prime. That's it. So whatever job A comma B does, there is someone else who can do the job for him. Or in other word, even if I take F minus AB, I have this property that for every xy there exists some set in F which will witness this. This is what I mean. Is this definition clear? Okay. So just apply this algorithm as much as you wish. Finally, you cannot apply this algorithm. Okay.
F does it stop? That I understood. For what is written here,
Yeah, which implies
for there can be some X prime, Y prime for which if I delete A prime, B prime, the family F.
I am not going to delete. I am just talking about useless for A. If there exists A comma B which is useless, then apply this. I am not saying every useless you do this. You do one at a time. Maybe I am useless now. Like, look, maybe there are several useless, but if I remove one useless, I can become useful. So you have to do this process iteratively. Every time the definition of which is useless is defined with respect to current F. It is not global F. Right? So this is why I say this. Right? Like now it's possible that in the second round, after I have done, now A prime B prime is no more useless. It was useless before, but once I deleted A comma B, A prime B prime is useful now. You get my point?
No, but we are saying if there exists, but one X pair of XY, right? But
Yeah.
there may be another pair for which AB is required.
Yeah.
So then how can we?
Okay, so not for all xy such that this happens, there is a sum. Okay, fine. Right. So all xy which A comma B takes care of, there exists some other A prime B prime which takes care of. Okay, and useless definition is defined with respect to the current family. So a set which is useless now, after deleting some other set, that could become useful. Okay. Okay, is all fine? So now okay. So now finally, after applying this process iteratively, okay, after applying this process iteratively, let F be a family where every pair is useful. Okay, every pair is useful because I couldn't apply this. What is the meaning of this? Let's write it. So suppose I have F1, F2, FQ. Okay, these are my partitions. Okay, okay, let's call it A1, B1, A2, B2, AQ, BQ. Okay, I cannot throw them out. What is the meaning of that? What is the bitness that A1, B1 cannot be thrown out? Meaning, what is the meaning of that? There exists a pair x comma y. So what is the meaning of this? I can't throw this. Implies there exists a pair x comma y. Of course, the size constraints are met such that x is contained inside A1, y is contained inside B1, and for all j greater than or equal to 2, okay, what is the property? Huh? What is the property? Both? Both? Both shouldn't hold, right? For all j greater than or equal to 2, it is not true that, what is not true? It is not true that x is contained inside A2 and y is contained inside, sorry, AJ, BJ. Okay? Okay. So now let's try to write down these sets and let's see what's the property of these sets are. I'm not sure if this proof with this way will hold, but let's see. Okay, I have gone completely different direction. So, okay, so let's write down x1, y1, okay, x2, y2. YQ. what can I say about x1, y2? I know that x1, y1 does not intersect, right? I know that x1 intersection y1 is empty, but does x1 intersect with y2? Hmm?
x1, y1, x2, y2, xq, yk all intersect with with the a1, b1 property. Like therefore, each of the individuals a1, b1 attribute to aq.
Can we find pair x2, y2 such that x1 will always intersect with y2? Can we find such witness?
y2 is a subset of
Hmm?
y2 is a subset of y1.
No, 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 no. I don't want that. What I want is the following property: xi intersection yj is empty if and only if I equal to j. Can I find such witness? Answer is yes, but I will leave you to think about it. Okay. So you got the point where we was getting it? I'll give you a proof for existential algorithm. This will lead us to a completely different technique in parameterized algorithm, which I thought it's a right time to tell you where it comes from. Okay. But I'll give you a different algorithm for 4 power k. Okay. So what did I do? So what I have applied is a very simple, greedy way to obtain an f, which we think that okay, definitely this does the job, right? But we have no idea what is the size of this f is. Okay, and if we can come up with a witness xi yi with the property, if I can come up with a witness xi yi, x2 y2, xq yk, such that this happens, okay, then we can apply some extremal combinatorics to bound it. Okay. So what do we want? By definition, they are non-intersecting because that is like among them. But I want the pairs so that x1 must intersect with every. And my question is, you can come up with such witness. Like, look, it was in our hand to come up with witness x comma y, which realizes the fact that f2 cannot be thrown. Okay? Okay. Okay.
If x1 intersection y equal to phi, then whatever pairs respects x1 y, that can be explained by x2 y2.
What you are saying? Come on.
x1 y2 intersection equal to phi,
Okay.
then whatever pairs respect by x1 y1, I can respect that by x2 y2.
Why? Suppose, what are you saying? Suppose x1
y2
is phi.
Now assume okay, a1 b1 respect by x1 y1,
A1 B1
b1
uh-huh,
by x1 y1,
x1 y1.
and I know that x1 intersection y2 equal to phi,
Hmm.
so a1 has no element in y2.
Exactly.
So a1 respect by
What?
a1 should must contain in x2
x1 intersection y2.
equal to phi.
Okay.
A1 has no element in y2.
Why? There could be some element in y2.
No, x1 intersection y2 equal to phi.
Okay. Yeah. x1 intersection y2
Equal
is
to
phi. Yes.
A1 has no element in
Y2.
So a1 must contain in x2.
A1 must
Contain in x2.
correct.
Yes. So
A1
must contain in x2.
May contain an element from y2.
no. So look, when you say that x1 intersection y2 is phi, this implies that what does that imply?
A1 intersection y2 equal to phi.
A1
Intersection y2
is phi.
So
Correct.
A1 must contain in X2.
A1
Must contain in X2.
No, but xy is a subset of a1. So there must be, there can be one element that is in
Why do we
y2,
have
y1.
one intersection?
Oh, sorry.
X1 is a subset of a1.
A1 intersection y equal to 5.
hmm.
Then A1 must subset of X2, right?
No, but why it is 5?
X2 Y2 is not the whole universe, no? Look, X1 Y1 is not a partition. So think, but it's there. Okay? But let me tell you something more funky, and that is good enough for our purpose. Okay? So how do I do? I construct my F as follows. My F1 is a random partition. F2 is another random partition. FL is another random partition, and I am done. Okay? Now I am going to give you that L sufficiently large if I take, I am good enough. Okay?
For constant there.
What do you mean? What?
I mean, since I am thinking about the algorithm that we defined earlier, random partition,
Yeah.
we found 4 power k times we found partition.
So let's see now what is the minimum L that I need. I know that L equal to something will works, but let's see what L will work here. What is the probability that F1, okay, so fix a pair x comma y, okay, fix a pair x comma y. What is the probability that F1, which is like rather than writing F1, okay, write F1 as A1 B1 AL BL, okay. What is the probability that say AI BI is good for x comma y, which is same as saying probability that x is contained inside AI and y is contained inside BI. What is this probability? X has size k and say y has size k. So x must go into AI, y must go into BI, and others I don't care. How many good partitions are there? How many good partitions are there? What? I thought it should be this. Is that fine? Right? There are 2 power n partition. How many of them are good partition? So the good part, okay, let's see. There are 1 by 2 power n partition. How many partitions are good? You fix x here, you fix y here, and the remaining you have 2 choices, right? So 2 power n minus 2k, which is 1 over 2 power what is this? It's 2k, no? Is that fine? Right? There are so many good things for him. This is what we choose. So with probability 1 over 4 power k, okay? Is that fine? Probability a particular thing. What is the probability? Right? What is the probability? What is the probability? So I am going to call what is the probability? So if I found this family and it is for every pair it is good, then it's great pair, no? What is the probability there exists what is the probability there exists a pair x comma y such that f is not good for x comma y. What is the probability, right? So, it is not good, it means this is not good and this is not good and this is, and we have chosen these functions independently, right. So, probability is not good is upper bounded by how much? How much? 1 minus 1 by 4 to the power k to the power l. Okay. For this is for a particular pair, right. Now, what is the probability that something is not good for there exists a pair? So, this family is not good for either this pair or that pair or that pair. So, probability that there exists a pair x y such that this is upper bounded by this. Is that fine? Look, how many pairs are there? Okay. So, I think it should be n choose how much? So, I choose first x, okay, or rather I choose, is this fine? N choose 2k, first I find these 2k elements and then I partition them, right? Okay.
I want size to be almost k each of
What?
x and y, both of them size should be almost k.
What?
The size of x and
Yeah, but they are not more than 4 power k, no? Who cares? Okay. So, probability that a family is bad is this. What I want? I want this probability to be strictly less than 1, because if this probability is strictly less than 1, what is the meaning? There exists a family for which this holds. Okay. So, for what value of L I can show this is strictly less than 1. Okay. So, what is my goal? Goal is to show is 4 to the power k, n choose 2k, let us say n to the power 2k, I do not care. Now, 1 minus 1 by 4 to the power k to the power L should be strictly less than 1. What is the meaning of this? If I choose some L is in our hand, right, which we have not selected. If we can select L appropriately, then we are great, right. What will that mean then? It means there exist L functions or there exists some L function which has the property that for every x y this is good. Not every L sized family is bad for me. Okay. I am not telling you how to find such a family. Now, all I am saying to you, there exists a small family. What should I choose L equal to? If I suppose I choose L equal to say 4 to the power log n. Let me choose this. Okay. Let us see what we get. Then what I am going to get? This is going to give you what? 4 power k n to the power 2k times is that fine? If I substitute L equal to this, will I get this? What is e power log n? N. So, n to the power k power 100. Right? Roughly n to the power, yeah. Which is definitely less than 1. So, even if I choose like, I mean k to the power 100 is a overkill, I mean you can choose some k square. So, all I am saying that I have shown to you there exists a family, right, of size 4 to the power k, some poly k times log n, and this log n is just used to cancel this n to the power 2k, there is no reason, right, because I want this family to be good for not only one x square, but for every possible x and y. So, what did we learn? There exists a family of functions or family of partitions of roughly 4 to the power k times poly k into log n size. If we can find that deterministically, or we can enumerate these functions, then our vertex cover algorithm is great. This is a real, what is it called? This is a real derandomization, because what is the meaning of derandomization? You look at the steps which the algorithm does. What is the algorithm does? It finds a partition randomly. Now, we have replaced that step with a partition provided by us, right. Now, to boost the probability, what did we do? We ran that algorithm several times, each time coming up with a partition chosen independently in that particular algorithm. Now, we replace this step with a, for every partition in my family, run your algorithm. If you succeed in any of these partitions, deterministically say, here is your vertex cover. If you fail, you deterministically say this. And what is the property of our function? That for any two sets and x and y of small size, I can separate them into my partitions. That's it. So, we can call this family of function as a separating collections with respect to k. Okay? And our probabilistic method showed that this is such small size family do exist, right. So, what did I show you? That there exists a q size family of partitions which has the property that for every pair x comma y, x is inside this, y is inside this. Okay? And there was another method which I was trying to do with this greedy minimal. Okay? Some point of time I will try to bring that back in discussion maybe after a month, okay? But keep that in mind, what you can do. That will allow one way to enumerate these functions, okay? But I will give you much more, let us say, a method of coming up with such families or functions which always works, okay? But that is for another day. Okay, right. Like how do you come up with these functions? Like how do I come up with such families of partitions? It's not obvious, right? Like in deterministic time, in time proportional to this in some poly n time, I want to come up with this family of functions. I want to write it down explicitly. We need some hash functions, something. We'll get there. But at least now you know one algorithm. Do you know one algorithm? Try 2 and choose q. I mean, at least look, this is a very bad algorithm. 2 power n choose q is a very bad algorithm. But what does it produce at the end? It produces a small family, right? This is the only known algorithm we can think of to construct this. So, we have to use this algorithm very wisely, when maybe like you do lots of divide and conquer, you do something, at the end when the universe becomes so tiny that this algorithm becomes polynomial, and you do this. Okay. For example, the universe is like log n, then 2 power log n, q is some other log, maybe triple log n, but it's still something even sublinear for that matter. Okay. So, we will get there, not going. But this was a general scope of things. Okay. This was, so all I wanted to tell you, the message which I wanted to pass is that these partitions has nothing to do with vertex cover. These partitions was all about two sets which I wanted to make disjoint. We just used it for the vertex cover. What happens if I assume that one part contains a vertex cover? Could we then come up with something better, something slightly nicer, right? That's where we will go. Okay. Okay. So, till you have any questions, I will let's wait for a couple of minutes if anybody has question. So, what we have shown up until now, that there exists a, okay, so let me at least write it down so that it remains in memory. So, what we have shown, okay, so what we have shown is the following. This is a lemma. Okay. So, if someone tells you, if you ever see some such kind of algorithm, okay, remember we also made a colorful algorithm, partition vertex cover. Who told us partition vertex cover? We randomly, if you recall correctly, we randomly colored those with 1, 2, 3, blah, 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 right? How do you know there exist some e power k such functions? Come up with random functions, right? What does a random function do? First one sets this, second one, try to do the same computation, you will see e power k popping out. Okay. Okay. So, lemma what we showed, okay. So, that lemma we showed, there exist, let U be universe on V on 2Vn, some universe, it has nothing to do with graph, okay. Let U be some universe, there exists a family of partitions U1, U2 dot 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 UL A1, B1, AL, BQ, there exists a family of partition of size 4 power k, k to the power big O of 1 times log n, which is very important, okay, such that for all x comma y, x comma y subset of universe mod x equal to k, y equal to k, x intersection y equal to phi, there exist ai, bi such that x is contained inside ai, y is contained inside bi. This is what we showed. This is precisely the lemma. There exists a family. We have not shown that how to construct this family, okay, but there exists a family. Okay. So, now having given you the motivations for this, so what kind of partitions we are looking for vertex cover, okay, what kind of partitions we are looking for. So, let us call this, we want to construct a VC family, okay, what we want to construct? VC family, let us call it VC family. So, VC family which takes a graph G, okay, takes a graph G, and what does it does? It outputs a vertex, it outputs a partition of Vg, okay, partition of Vg again A1 B1 AL BL, what is the property? Such that okay, such that for all x y, we will make what it is, x is a minimal vertex cover of x, x is a minimal vertex cover of G of size how much? At most k, and y is a subset of Vg minus x, okay, y has size at most k, and n of y is equal to x. This is what we want. So, I want such partition. How do I go about finding such partitions? Makes sense, no? Right? Like why do I care about, maybe finding this general partitioning could be a difficult task, but maybe for the vertex cover we could do an easy task, okay. And let me show you how do we find this easy task, and then from easy task we will go to an easier task, okay. It is very simple, finding this is very simple. Let us see. Okay. All I tell you, let Z be a vertex cover of G. Z is a vertex cover of G. Okay. Z is a vertex cover of G. Okay, any vertex cover. We'll worry about this later. Suppose cardinality of Z is T for now. Okay, doesn't matter what it is. Now, I don't know these things. Okay, but what I want. Okay, let's fix some x comma y. Fix x and y. This is z and this is I, z minus z. Okay. Now let's look at where x will lie. X is going to be where? X could be somewhere here and maybe somewhere here, right? Okay. But I don't know which one of them is this. Okay. So let's try to build. So let's, for this I want to build say some A, potential A comma B, I'm trying to make. Okay. I said okay, I don't know, but like first of all A must contain Z intersection S, X is contained inside this. Agreed? Fine. Is it fine? Now, what is Z minus X? Look at this. Look at X contains this and contains this. Imagine yourself deleting this from the graph. This is independent set, but what more? What is the, where is the remaining X? Can I find now? Neighbors of Z minus X. So don't I know now? Right? So what does A contains? Z union X, Z, not sorry, what am I writing? Z intersection X and neighborhood of Z minus X, right? This is what my A is, right? Think for a minute. Then what is B? Very simple, no? Those not in A and in VG. That's it. So how many such partitions we made? This is my family. What's my family? My family is, so now let me give a description for this family, right? It's very simple, right? I just use the definition itself in the definition. Z be a vertex cover of. If I give you a vertex cover of G, how can you construct this? I have not told you how to find this Z. I will come to that. We will see in a minute, no? Don't worry. We will come to that. Okay. Okay. So what is my family? My family is, now given Z. Okay. What is this? What is my family will be? Right? It is going to be Z1, okay, and union neighborhood of Z1, right, comma Vg minus Z1 union, and for all Z1 subset of Z, and Z1 has size at most k. That's it. Yeah. So I don't know what is Z intersection X. So I'm guessing. I'm saying, okay, let's try all possible intersection of this. I don't know which one of them is. So I'm going over all Z1 and to that I am adding neighborhood of Z1, whatever that is my one part, and the remaining is other part. This is exhaustive. Given this is just an exhaustive description. What is the size of this? In the worst case, 2 power t. Huh? What should be there? Okay, my bad. You are absolutely correct. This is what it should be, right? Then, and suppose this I call A1 minus A1. Okay? Z1 subset of Z, because that is all that I was trying to care, right? So, Z1 is intersection of some k size object. So, why should I take more? Done. So, if I give you Z, you can construct this, and what is the size of this? If the size of this is t choose k. Okay, that's it. So, which is at most 2 power t. Okay, of course, 2 questions. How do I get Z? Can anybody tell me how to get Z? Is it that hard? Take a maximal matching, take both endpoints. What is its size? 2k. If its size is more than 2k, say no. Like empty set, nothing happens, you are perfectly fine, right? So, Z you know how to get, no? So, what is Z? Find like 2 approximate vertex covering, right? If the size of Z is more than 2k, empty, else Z is less than or equal to 2k. So, 2k choose k is this. So, what is the size of this? 4 power k, absolutely 4 power k. So, my first part was that is true in general, okay. But if you give me vertex cover, I can do more things. I mean, I could be more smarter, I could do things easier. So, digest it, okay. We will move now. But if I would have given you Z of smaller size, what would happen? We will get something smaller, no? Smaller family, smaller algorithm. So, if I could give you, okay, if I could give you, okay, so is the idea clear? Right, this is my VC family. I will keep the definition so that you can keep looking at it as much as you wish. Okay, okay, is this fine? But notice, I am going to remove this and keep this, because this is all that the picture is important. That is my definition, this is my family. Okay? Please, if you want to note down, note down. Okay. Now, if I gave Z of size some k plus 1, what will be my family size then? And there are clever ways of doing this also, we will get there, that is the whole point. How do I get this k plus 1 size solution? Here is a trivial way of getting a k plus 1 size solution. What is a trivial way of getting a solution? It is the following. Let us run a recursive algorithm. Can I write a recursive algorithm? Induction, 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 induction. Let us do induction. I delete a vertex, remaining graph, find a vertex cover of size at most k if it exists. If it not, if it exists, it gives you a k size solution, no? Then if I add this vertex, what happens? I have got my family, no? And given this family, I know how to find my minimum vertex cover algorithm. Am I done? Okay. Okay, let me wrap this. Here is my algorithm. Okay, here is my algorithm. Okay, what is my algorithm? it is VCG okay. Maybe I have not written recursive algorithm for long, so it may take some time. So let us say MVC, it takes a graph G, maybe a number k, and it does something. Okay, let's say. Okay, if vertex set of G is more than k, okay, VC is G minus U for some MVC this is it. I know I am on purpose writing it very badly, but like if the size of my graph is more than k, what I do? I delete a vertex, I say, hey, you go, right? So I need some base case. Okay, I need some base case. So so what I am saying, if Vg is strictly more than k, it is what? MVC G minus U k. That's my subroutine. So and this recursive algorithm, it calls itself. So what is my base case? If Vg is equal to k or less than equal to k, return yes, okay, and suppose it returns some solution S, and yes and S equal to Vg. Right? So what will happen when I come here? Okay, either I will come here. Okay, so if I come here, right, what I have a solution S of size k. Right? If I return here, what do we have? Let S equal to, in the beginning, S union V, right? So so it returns something, right? Either it can return yes or this, right? So I check if MV or okay, if so it can return no. Okay, so what should I write? If equal to no, if this is equal to no, what you do? You also return no. What is the meaning of this? That there is no minimum vertex cover of size at most k for G minus V. The can G has a minimum vertex cover of size has a vertex cover of size at most k? No. So this is, if this returns no, then this. Else S equal to, so it has returned a minimum vertex cover of size at most k. Now let Z equal to S union V. Okay, run my family algorithm, run the family algorithm, right, run the family algorithm, okay, run the family. If any return solution of size k, return that as S, else return no. Okay, I am not a great in, but this is just a recursive algorithm. It is an induction algorithm. Okay, what is an induction algorithm? I say, hey, look at G minus U. Either G minus U has a solution of size k or it does not have a solution of size k. If G minus U does not have a solution of size k, please for yourself say that you do not have solution of size k. Or it has returned you solution of size k, now you have that extra vertex, you add that forms a vertex cover of size k plus 1. Now I can run my family algorithm and I am done. Okay? Those I know those who have seen this before will realize what this is. Do you realize what it is? But I don't have to tell you this. This is a recursive algorithm. No? Okay. Isn't this the more natural? That what happened? Like, okay. So what happened here? Okay. Now I will make you a different version of this algorithm. Okay, which you will see, which you might see. But it is important to see from where do they come. Okay. So what happened? So what does G does? G calls its algorithm in G minus U. Okay. Now G minus U returns two things. Says returns no, meaning no vertex cover of size at most k. Then what does G does? This implies G returns no vertex cover of size at most k, which is perfectly fine. If G minus U itself, I can't find a vertex cover of size at most k, there is absolutely no hope to find a vertex cover of size at most k in G. Or returns S, that is vertex cover of G minus U of size at most k. In this case, G has S union V, a vertex cover of size k plus 1. And then what does it does? Okay, now that I have got a k plus 1 algorithm, let me find out with help of this that whether G has a vertex cover of size at most k or not. This is what this does. This is what the family algorithm does, right? So given any graph, if you give him a family of size 2 power k plus 1, it can check in poly time whether this is. So how much time does this algorithm takes? How many times are you running this algorithm? N times, n minus k times actually. Like what happens if you look at this graph, look at this algorithm. This algorithm does nothing. Okay, if you look at this recursion, it does nothing. Okay, so let's unroll this recursion. What happened? I had a graph G minus say U1, and let's call this G1. Next, what happens? I have G2, which is G minus some U2, dot dot dot. Look at G n minus k plus 1 graph. What happens in this? This is एक vertex निकल गया. So G minus G n minus G2 has 2 vertexless. Okay. So I want n minus k. So it is minus 1 minus U n minus k minus 1, right? It goes up to here. Now what happens at G n minus k? It finds it has k vertex, right? What does it do? Okay, it rolls back here. Now you trace back, it rolls back, right? It rolls back here, okay? It rolls back here, it's returning yes, and it returns all its vertex set V G n minus k as S. This is what happens here. Now when it comes here, he has a solution of size k plus 1. It either returns no here, either returns no, or in 2 power k plus 1 times returns S. Same here, same here, same here. So what's the total running time of this algorithm? It's 2 to the power k plus 1 times n to the power big of 1. That's it.
If this algorithm returns no, like then there doesn't exist a vertex cover of size.
Of course not.
Because we are like deleting the vertex arbitrarily.
So what? Imagine yourself, if G had a vertex cover of size at most k, any induced subgraph has a vertex cover of size at most k. If an induced subgraph has no vertex cover of size at most k, can G has a vertex cover of size at most k? Then that's it, no? It has nothing to do with arbitrary or anything. It has, you don't have to be smart, that's all that point is. You need not be smart. Okay. So now that we have written this recursive algorithm and we have unrolled, now if you can unroll it, people do it slightly differently, okay? Then people will tell, but in my head this is an induction. Why it is an induction? By inductively, if I had a solution of size k, right, it implies at this step I have a solution of size k plus 1. Can I use that to get a solution of size k or not? Right. So at any stage, inductively you are saying for the smaller graph, I have a correct output of my algorithm, either no or a solution of size k. If it is no, then I can correctly say that, oh, because induced subgraph has no, it means whole thing has no. If it has a solution of size k, I get a solution of size k plus 1 and I try to take help of this k plus 1 size solution to see if there is a solution of size k or not. Right. So this is why this routine is called compression routine. Why? Because you are trying to, given a solution of size k plus 1, you are trying to see if there is a solution of size k or not. So you are trying to compress a solution of size k plus 1. Okay. So what happens as a routine at any point of time? Okay. So as a routine, every time given a solution of size k plus 1, check whether we have a solution of size k or not. Right? This is called compression routine, right? Because you are given a large solution, you are trying to compress whether there is a smaller solution or not. So this is why it is called compression routine. Okay. Now this is a recursive algorithm, right? And this is what this does, right? So basically what it does, this is basically here compress. So I will have a routine here who says compress G, this graph comma Z. So I have given a small solution or a bigger solution, it just try to compress here. So this is basically our compression routine. Okay. Now rather than going from top down, we can also go bottom up, and this is what is called iterative composition. Okay, it's the same thing. So what I mean by this, so you keep this and now you say okay, now rather than going this, I could say let's V1 to Vn be an arbitrary ordering of vertices. Okay, arbitrary. And what is graph GI? Graph induced on first I vertices. Okay, right? So now you will look, you will have a loop from I equal to k plus 1 to n, and what will you do? You will do the same thing, right? Like you check, right? For I equal to k plus 1 to n, right? I will check. So what is a gk plus 1? It has a vertex cover, say sk plus 1, which is basically v1 to vk plus 1, right? Now what will you do? Say okay, apply compression routine. Okay, apply compression routine. Okay, what will happen after compression routine? After compression routine, either we will get return no, right? Compression routine can return no, right? No. Then what? You also return no, or it returns some s, right? It returns s of size at most k, right? So now next stage what will happen? You have s of size k, you will add the next vertex and then you have a another sk plus 2, right. So, basically what happens is that you have a graph g1, g2 dot 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 gn, right. Now, at any point of time you are looking at graph gi, okay. Either it says no or it returns a f of size k. If it returns no, no everywhere, else what is gi plus 1? Gi plus 1 is like sk si plus 1, which is s union vi plus 1, okay. Just do the same thing. So, rather than doing like down, you are doing bottom up. So, you are iteratively trying to compress the solution, and this is why people call this routine whole method iterative compression, okay. So, if you like recursiveness, this is what you should keep in mind. If you like iterativeness, you keep this in mind, whatever you feel appropriate. But at the end of the day, it is an induction, right. For a smaller solution, smaller instances, inductively I have built a solution. Can I use that solution? Can I take help of that solution to build a solution for a larger instance, right. So, here you dealt with up to I, right. In the next stage, you are dealing with I plus 1 vertex. Next stage, you are dealing with I plus 2 vertex. So, inductively, you are trying to build your solution. And this induction has nothing to do, I do not have to construct this graph vertex by vertex. I could construct this graph edge by edge. I could construct this graph, initially I contract all the edges to a single vertex and then I decontract one by one edges. I could do any operation, right. Induction has nothing to do with just one vertex operation. I could apply any vertex operation and start from this, the smallest graph, and whatever operations I have applied to get this graph, I unroll it and do my induction on that, right. So, I can design this algorithm on any of these methods, right. So, for example, when we try to design certain algorithm, we say, okay, fine, let us find a matching. If the graph has big matching, find it, contract both endpoints. Graph certainly will have lot less vertices, half vertices. If I had a perfect matching, what is the number of vertices? Certainly n by 2. Maybe I can find a solution there. Now, unroll it, and if I can do something nicely with this unrolling of solution, I am great, because when I contract lots of vertices, what happens? I started with n. In the second instance, how many vertices I have in the graph? N by 2, n by 4. If you sum this up, it is not more than 2n, right. So, this is a way to design linear time algorithm in many cases, that this will never give you linear time algorithm in certain sense, because every time you are only decreasing the graph by one vertex. So, you have to apply the compression routine at least n times. But if I wanted to only apply compression routine, say log n times maybe, then I do some n by 2 something, apply it once more, 4. So, you only have applied small number of time. So, I mean, all I am trying to tell you is that there are several ways to be smart, okay. So, the whole idea is, if I have a graph, if I have a problem, what is the right way of inductively building this graph? And if I follow that inductive process of building this graph, okay, I follow that inductive process, and given a solution for a smaller inductive graph, for the next graph, I use help of this already built solution, because that already throws away lots of solution, throws lots of structure to my input. Can I exploit that structure to do this? Now, tomorrow morning we will see how many ways to. So, this was one way to get, right. Like these are the two ways to get you solution, right. I have actually told you 3 ways to do this. First was approximation, find this 2k, right. Then do I need to do, how many times do I need to do compression routine? Should I need to do anything for n minus 2k vertex? Nothing. I could build my graph starting from just this, look at this n minus 2k independent set, I know it has a vertex cover of size at most k, now one by one. So, this way also I can minimize the number of times I have to call my routine. So, if I had a good approximation algorithm, I compute that, and then I run my compression routine, which tends to be bit more expensive, but not more than poly time, but then I can minimize it. Or I could apply this recursive procedure, or I could iteratively construct my solution. Okay? But at the heart of every such algorithm is what? Not the methodology itself. The heart of algorithm is compression subroutine. This is the heart. Heart of all our algorithmic idea is a compression routine, not whether you do recursively or whether you do iteratively or whether you do approximately. It doesn't matter. Okay? What matters is if I give you something, how can you compress it? Okay? Okay. So that's all that I had to tell you today. I'll tell you the rest tomorrow. We'll continue with our discussion in the morning.